Hello everybody, and welcome to the top of page 49. In this video, we're going to be working through example 3, and this is going to lead us into the most important definition of this section. Okay, so what do they give us in example 3? Well, they're starting us off with a linear transformation t from R2 to R2, and they give us a formula for it. And we can make kind of an interesting observation about this linear transformation. Okay, this right-hand side can be rewritten in kind of an interesting way like this, using matrix multiplication. 1, 2, negative 1, negative 3 times the vector x1, x2. You can check this by just doing the matrix multiplication over here to the right and confirming that if you do that multiplication, it gets you back to this, the formula that they gave us. Okay, so what this says then is that we can describe this entire linear transformation as multiplication by a matrix. Okay, I'm going to write that out in words. That's an important observation. So t can be described as left multiplication by the matrix A equals 1, 2, negative 1, negative 3. We saw that above. Okay, so kind of in symbols, we could write this then. T of a vector x in R2 looks like that matrix A that we just wrote down times x. We're going to introduce a piece of new notation, LA of x. That means in words left multiplication of x by A. Okay, I'm going to just add that to our work here. So LA has a name. It's called the left multiplication operator. Okay, we'll see that come up now and then as we continue with our course. Okay, so far what's kind of interesting about this is that this particular linear transformation can be completely described by this matrix. Those four numbers contain all of the information that we need to do a calculation, to substitute something into our transformation and get a result out. Okay, there's one other interesting observation that we can make, and this is going to lead us to our definition ultimately. Notice what happens if you plug in the two standard basis vectors for R2. Okay, if we take t of 1, 0, then x1 is 1 and x2 is 0. If we go over here to our definition, make x1 1 and x2 0, we're going to get out 1 and negative 1. Okay, and then similarly, if we go to the second one, t of 0, 1, okay, and make x1 0 and x2 1, okay, up here in our definition, we're going to get 2 and negative 3. Do you notice anything special about those two results that we got? Okay, here and here. Notice that those are the columns of our matrix, right there. Okay, so let's write that down. This is the first column of A, and this is the second column of A. So this matrix here, A, that we just mentioned contains all of the information of our linear transformation. We can get that matrix by just substituting in basis vectors, vectors in a basis that build our domain. Okay, and it turns out we can play this type of a game for any linear transformation that goes between finite dimensional vector spaces. That's what this definition is about. Okay, so let's read through the definition, kind of using example 3 as a motivation here. So let V and W be finite dimensional vector spaces. Okay, and let T from V to W be a linear transformation. And then we're going to take two bases, beta, V1 through Vn, that's going to be a basis for our domain V, and W1 through Wm, that's going to be a basis for our codomain W. Okay, and what we're going to build is an m by n matrix that looks like this. A equals, okay, and bear with me, this notation is going to look a little confusing at first. So we're going to take the coordinate vector of TV1 relative to our output basis. Okay, that's going to be a column vector. That's going to be the first column of our matrix. Then we're going to do the same thing for V2. Take T of V2 find its coordinate vector. That's going to be the second coordinate, or the second column of our matrix, and we continue until we get to the last basis vector in beta. T of Vn gamma. Okay, that's a column vector. And so that's a lot of notation that I'm throwing at you here, but the one thing I'd like you to notice up to this point is that these columns are just coordinate vectors. Columns are coordinate vectors. And our motivation for doing it this way is exactly what we saw up in example 3. These two vectors, 1, 0, and 0, 1, they form a basis for our domain. And v1 through vn, they form a basis for our domain down here, v. Okay, so we just took those vectors, v1 through vn, one at a time. We calculated t of those, and we used those coordinate vectors as columns in our matrix. Okay, so this matrix that we just wrote down has a name. It's called the matrix representation of T in the ordered bases beta and gamma. Now that's kind of a mouthful saying that, so we'll abbreviate that by just saying the matrix of T. Okay, and then this is a matrix we're going to be doing a lot of calculations with, so we'll introduce some notation. We're going to write A like this, bracket T beta gamma. And the way that you would read that is the matrix of T taking beta coordinates to gamma coordinates. Okay, now there's one special case that we'd like to talk about. In some cases, this linear transformation that you start with, it might be the case that V and W are the same vector space, and that you choose the same basis for the domain and the codomain. And in this case, we're going to abbreviate the matrix and write it like this. Just T of beta. Since there's only one basis, we won't write T of beta beta. Okay, we won't write the beta twice, we'll just write it once. Okay, now it's easy to look at this definition and get confused. I mean, there's a lot of notation, and to get a sense for what this is really saying, you need to see some examples, okay? So in the next few videos, we will be very slowly kind of unpacking this definition, doing some calculations, and trying to make sense about what this definition is telling us.